this is 34th lecture, and we are discussing coalition interaction. It is basically the 5th module of this. And today we are going to talk about what we are going to discuss the 30th lecture, that is dispersion, attenuation of waves, and damping. So when we talk about dispersion and attenuation, this will be waves, and then when we talk about damping, it will be both metal damping and radiation damping. Like the 5th module of the course, that is on SSI 4D. And in this 5th module, we have already covered 3 chapters, that is introduction to soil interaction, facts of soil interaction. Then we also talk about strong ground motion and wave propagation, and we discuss wave, that is the 4th one. We are going to talk about first dispersion and attenuation of surface waves, and then damping. So let's have this 4th chapter on SSI, and which is very important for earthquake resistant design of foundations. What we are going to discuss today. Here, when we talk about dispersion and attenuation waves and damping, these are the topics which we are going to discuss. One will be dispersion of surface waves, then it will be phase and group velocities, then it will be attenuation of surface waves, metal and radiation damping of soil. All 4 will be discussed. So let's start from the first one, that is the dispersion of surface waves. What is the dispersion? First of all, this is phenomena, the wave, which will be applicable for surface waves only. In the last lecture, which we have discussed, that earthquake is nothing but release of energy through elastic waves in the earthquake. And there are 2 types of elastic waves. One is called body waves, and another is called surface waves. Within the body waves, we have 2 types. One is P wave, and another is S wave. And then you have the surface waves, where we have discussed again 2 types. One is called relief wave and love waves. So within the category of surface waves, this phenomenon of dispersion occurs. And what is that dispersion, which we are going to talk about that. So here, first of all, when the relief wave's velocity in a homogeneous half space is independent of frequency, so that is key. If your medium, soil medium, is homogeneous, it is not heterogeneous. In that case, not only body waves, of course, body waves will be traveling independent of frequency, but even relief wave will also, their velocity will be independent of frequency. However, on the other hand, the velocity of love wave varies with frequency between an upper and lower limit. So irrespective of the type of medium, the love waves will be dispersive. Love wave frequency velocity will be changing with frequency. On the other hand, relief waves velocity will remain constant in a homogeneous medium, but will be changing in heterogeneous medium. So what is dispersion? Dispersion is a phenomena in which waves of different frequency, or we can say at different wavelength, propagate at different velocities. So means if you change the frequency of the wave, then its velocity will also change. Then this phenomena is called dispersion. And the love waves are dispersive in nature, and relief waves in a homogeneous half space are non-dispersive. So within the surface waves, love waves will be dispersive irrespective of whether they are traveling in homogeneous or heterogeneous medium. But relief waves are dispersive in case of no heterogeneous medium, but in case of homogeneous medium, they are non-dispersive. That means there is no change in their wave velocity with frequency if it is traveling through the homogeneous medium. But because in general, you know that in real scenario, this Earth is a heterogeneous medium. So in that case, because it is rarely homogeneous medium. So in that case, in the real situation, both relief wave as well as love wave will be dispersive in nature. So this was about. Continue with that. Relief waves, now coming to when you have, you know that when you have long wavelength, that means you will have low frequency. And if you have the short wavelength, then in that case the frequency will be high. So if you have a relief waves of long wavelength with a low frequency, they can propagate faster than relief waves of short wavelength. which is for high frequency. Therefore, in the real world of heterogeneous materials, RLF waves are also dispersive, because as the wavelength changes, then there is a change in the frequency, and when there is change in frequency, then there will be wave velocity will also change. Now, since the velocity of both RLF waves and love waves decrease with increasing frequency, the low frequency components of surface wave produced by earthquake can be expected to arrive at a particular site before their high frequency counterparts. And this tendency to spread the seismic energy over time is an important effect of dispersion. So within the same type of wave, let's say you have surface wave, which is a RLF wave and love wave. Now within the same wave, if the frequency is changing, in that case, low frequency component of the wave will arrive at a site faster than high frequency component. And the reason being that low frequency component of the wave will have the higher wave velocity compared to high frequency component. Or in other words, you can say, because when you have low frequency component, its wavelength will be higher. As the wavelength is increases, then its wave velocity will be higher. So this was all about dispersion of surface waves. And let me summarize again. Dispersion is a phenomena where the wave velocity is changing with frequency, number one. Second thing, for body waves, you don't have this effect of dispersion. Dispersion will be applicable only for surface waves, and in real heterogeneous medium, both RLF wave and love wave will be dispersive in nature. Okay. Now, there is one what is called phase and group velocities. When the waves travel, then two types of velocities are referred. One is called phase velocity and another is group velocity. So, and again, when we are talking about that, this is related to again for surface waves. And for the surface waves, the solution for RLF wave velocity, which is denoted as V subscript R, and love wave velocity, which is denoted V subscript L, are based on the assumptions of harmonic loading, which produces an infinite wave frame. So the solutions which is calculated for RLF wave and love wave, they are based on harmonic loading. Now, these velocities describe the rate at which points of constant phase, for example, peaks, troughs, or 0 points, travel through the medium and are called phase velocities. So you have, let's say that when we say the constant phase means you can say that points, which is maybe either it could be pick up, troughs, or 0 points. So these points, whether you say, let's say, peak of a wave is traveling with some speed. So if they are traveling, like you know that this point itself will call phase, and if you refer that the velocity of some peaks or some trough or some neutral points like 0 points, then that velocity for a particular wave will be called phase velocities. And phase velocities, in the sense, it could be RLF wave velocity or love wave. But this is related to a single point. Now, a transient disturbance will produce a packet with similar frequencies, and this packet of waves travel at the group velocity. First of all, this packet of waves are frequency is in the similar range, number one. That is not very much different, because once the frequency gets changed, naturally the wave velocity will be different. So the packet of waves with similar frequency contents that travels together, and their velocity will called group velocity, and group velocity Cg, which is given by this relation, Cg equal to C plus K dC by dk. Here, what is C here? C, small c, is called the phase velocity, and this phase velocity could be either Vr and Vl. K is called wave number, and let's discuss in the next slide. So where C is the phase velocity equal to Vr or Vl, depending on which type of wave is being considered. If you are considering RLF wave, then it will be Vr. If you are considering love wave, then it will be Vl. And K is the wave number, and this wave number is equal to what is called K equal to omega by Vr or omega by Vl is the case applicable, where omega is frequency of excitation. So this is the wave number. Now, in a non-dispersive material, this dc by dk, where c is the phase velocity and k is wave number. So this dc by dk will be 0. So the group velocity is equal to the phase velocity. So once you have this non-dispersive material, then in that case, Cg and Cc will be the same thing. However, when you have a dispersive material like for heterogeneous material, since both materials generally decrease with increasing frequency in geologic materials, which we have already discussed, when the frequency increases, the wavelength will decrease, and wavelength decrease, then wave velocity is expected to decrease. So as a result, because C decreases with K, so this dc by dk is negative, or it is normally less than 0. As a result, using this relation, when dc by dk is negative, so Cg will be smaller than C. So that means the group velocity is lower than the phase velocity. So normally the group velocity is lower than the phase velocity. So that comes out of that. Now this was all about what we have discussed so far. We have discussed dispersion of surface wave and then phase and group velocity. Now another phenomena which is more relevant for surface waves, and that is called attenuation of surface waves. And what is that attenuation? You know that attenuation, what is the literal meaning of attenuation? Attenuation is to get reduced in amplitude. So for example, if you have a source of a light, or if you go away from the source, from electricity power, and the light's intensity get diminished. If you move away from some tube light or some bulb, so what that is called attenuation. So, and that is with the distance. So as you go away, the amplitude get decreases. Same thing happens in case of elastic waves of earthquake also. As you go away from the source, the amplitude will get decreased, and this will be called attenuation. And this once decrease in amplitude, so and obviously this decrease in amplitude will depend on the material through which the waves are traveling. So for example, in a homogeneous linear elastic material, the stress waves travels indefinitely without change in amplitude. So if you consider ideal condition, that soil consists of a homogeneous material and it is linear, not and elastic also. In that, if this condition satisfied, then we can assume that the stress waves are traveling without change in amplitude. But this is not the case, and this type of behavior cannot occur in real materials. The amplitude of stress wave in real materials, such as those that comprise the earth, attenuate with the distance. And this attenuation can be attributed to two sources, one of which involves the material through which the waves travel, and the other the geometry of the wave propagation problem. So you have two sources. So when we talk about this attenuation, that means it is one which is when these waves are traveling through some material. So what happens? The material, let's say soil, absorbs some energy, and this is called material damping. In fact, you may be aware what we mean by damping. Damping is basically nothing but dissipation of energy. If we talk about damping only, so that is when the damping is present in the system, that can be defined as a dissipation of energy. Dissipation, D-I-S-S-I-P-A-T-I-O-N, dissipation. Of energy. Now, this dissipation of energy can be in two forms. One is that when the waves are traveling through certain material, then material may absorb some energy. E-N-E-R-G. 1 minute, please. And another things could be that when the waves are traveling through, they are spreading in this large medium, that is the geometrical spreading, and then in that case it will be called radiation damping. Now when we talk about attenuation metal damping, in real materials, part of the elastic energy of a traveling wave is always converted to heat, and this conversion is accompanied by a decrease in the amplitude of the wave. So, and viscous damping, by virtue of its mathematical convenience, is often used to represent this dissipation of elastic energy. So you have this case of first thing is this. Let's go back. So you have metal damping and radiation damping. Now let's discuss about only metal damping only. In case of real material, which is normally heterogeneous metal, part of the elastic energy of a traveling wave is always converted to heat, and this conversion is accompanied by decrease in the amplitude of the wave. Viscous damping, by virtue of its mathematical convenience, is often used to represent this dissipation of elastic energy. Okay. So normally viscous damping is used because it is mathematically convenient to represent the dissipation of elastic energy. So this is the dissipation of elastic energy, and this dissipation of elastic energy itself is called damping. So this is damping. This is nothing but damping, and this damping is due to here, because this is due to the material, so it will be called material damping. For the purpose of viscoelastic wave propagations, soils are usually modeled as Kelvin-Vogel solids, that is, materials whose resistance to shearing deformation is the sum of an elastic part and viscous part. So here, what is called Kelvin-Vogel solids. Kelvin-Vogel means you have a spring as well as a dashpot. So spring provides the elastic component, while dashpot provides the viscosity component. So what is here? So to represent the material damping here, what you could see, there is a layer of the material. Within this layer, the connection, this can be represented with a spring with a stiffness G, shear modulus, and eta is nothing but viscosity. So this element is subjected to shearing. Shear force is applied, shear stress is applied, thickness of the element is dz. So the movement of one is du. So what you have here, thin element of a Kelvin-Vogel solid, which is subjected to horizontal shearing. Total resistance to shearing deformation is given by the sum of an elastic spring and a viscous dashpot component. So what you have here, first of all, the total resistance will be coming from this spring as well as viscous dashpot, and this total resistance can be represented by here total shear stress G multiplied with gamma plus eta into del gamma by del T. Why tau is nothing but tau xz is the shear stress acting in xz plane, which is perpendicular to y plane, and gamma is shear strain, which can be represented by del u by del z, where u is the rest displacement, is the shear strain, and eta is the viscosity of the material. Here one can understand that the shear stress is the sum of an elastic part, which is here elastic part, and this elastic part is proportional to strain gamma, while viscous part is proportional to strain rate. Okay, so G multiplied by gamma plus eta should be multiplied by not gamma, del gamma by del T, which is the strain rate. So the total shear stress will be coming from two components. One is elastic, another is viscosity, and this is what is called viscous damping. Now coming to this, normally the damping is represented in terms of what is called damping ratio. This is a dimensionless number, and it is a ratio only. And in this case of damping ratio, normally for viscous damping, damping ratio notation is given by chi, and this is related to what is called the force displacement or stress strain loop as shown in this figure. So what you have is stresses loop is there. In this stresses loop, what you have is here, the total area of this loop is denoted as del W. So energy dissipated in one cycle will be del W, and the peak energy of this triangle will be W, capital W. So the peak energy is the area of this triangle. So the ratio of del W by W divided by 4 pi gives you that damping ratio. Okay. So the damping ratio is defined from this relation, and as the area of this loop increases, let's say for even for the same value of W, then the area may get changed. Then area of this loop increases, the damping ratio will increase. Okay. To continue with that, now the peak energy stored in one cycle is denoted W, capital W, and capital W is half E gamma naught square. And with these, damping ratio is given by 1 by 4 pi del W O W eta W O 2. To eliminate frequency dependence while maintaining the convenience of the viscoelastic formulation, above equation is often rearranged to produce an equivalent viscosity that is inversely proportional to frequency. Here, damping ratio is dependent on eta omega, that is the frequency of excitation. But normally, an equivalent damping ratio is found out using equivalent viscosity if I put the value of eta in such a way that eta is inversely proportional to omega. In that case, eta omega will be constant and eta omega will not be varying, and that form of the damping ratio will be called static damping ratio. And use of this equivalent viscosity ensures that the damping ratio is independent of frequency. So this was about material damping. Now, beside material damping in the soils, there is one more term which is called radiation damping or geometrical damping. And that is very important, because in case of structures, you have mostly material damping only, you don't have the radiation damping. But in the soil, if you neglect the radiation damping, then it could be, the results will be very much erroneous. So let's consider what is the radiation. Since material elastic energy of stress field, the specific energy, which is nothing but elastic energy per unit volume, decreases as the waves travel through a material. Okay, so specific energy got decreased as the waves are traveling through the material. The specific energy can also decrease by another common mechanism, which is pure geometric origin, resulting from the decrease in specific energy that occurs as the area of the road increases. So in the first case, the specific energy decrease because due to material properties, because due to some absorption of the shocks by the material. But in the second case, the specific energy decreased due to the spreading of the waves. And this reduction in amplitude due to spreading of the energy over a greater volume of the material is often referred to as a radiation damping, and it is also called geometric damping or geometric attenuation. So whether you call radiation damping, geometrical damping, or geometric attenuation, all three are the same thing. Okay. So continue with this. When earthquake energy is released from a fault below the ground surface, body waves travel away from the source in all directions. Okay. So when you have let's say some source of disturbance, which is called focal point, in that case, when earthquake energy is released, then body waves will travel in all directions. It can be shown that geometric attenuation causes the amplitude to decrease at a rate of 1 by r. So what will happen here? So geometric attenuation will, due to this geometric attenuation, the amplitude will decrease, and this decrease in the for the body waves is at a rate of 1 by r, where r is the distance. So that means when the r will increase, the amplitude will decrease, or you can say that the amplitude of body waves is decreasing inversely proportional to the distance. Okay, so more the distance, more attenuation it will be there. But when you talk about surface waves, then also with the distance there is a decrease in amplitude, but this decrease in amplitude, it is at a rate of 1 by square root of r. Okay, that means here this is 1. Let me put like this. This is not I. Okay, 1 minute. This should be 1. 1 by root r. Now, in other words, surface attenuates much more slowly than body wave, because here this will be 1 by r will be decrease at a rate of 1 by r. So there will be for body waves, because r is distance which is more than 1. In that case, you know that the decrease for body waves will be higher than the decrease in the surface waves. Okay, because r is greater than root r. So 1 by r will be less than 1 by root r. So this is the final product. If you multiply by 1 r, then you get the final amount of the amplitude. Same thing is here. So r is greater than 1 by r. That means 1 by r will be less than 1 by root r. Okay. So that means decrease here will be more compared to in this case for surface wave. So that's why it can be explained that there is a greater proportion of surface wave motion related to body wave motion, which is commonly observed at large epicentral distance. So when you have the large epicentral distance, then the amplitude of surface wave is higher than the body wave. So it can be explained. Continue with this. For problems in which energy is released from a finite source, ranging from the large scale case of rupture along an earthquake fault to the smaller scale case of vibrating foundation, radiation damping can be extremely important. In such cases, the effect of radiation damping often dominate those of material damping. So this was about radiation damping. Thank you very much. And today's lectures content was mostly from these references. It is mostly from the second reference, that is the book by Kramer, and which is Geotechnical Earthquake Engineering, titled Practice Hall Publisher. So the speaker is thankful to these authors of these books, and these have been used as a research material. Thank you very much for your kind attention.